All right, but now, so this is the whole thing. This is what we want to get from this. Is this whole idea of dimensions, right? That everybody's wrapped around the axle with. See, so I took this from the music man. Total starts with capital T, and that rhymes with D, and that stands for dimensions, extra dimensions. That is not pool, but extra dimensions. And so string theory needs 11 space-time dimensions. Supersymmetry needs another quantum dimension for every string dimension. And then M theory takes another quantum dimension because of the supergravity and whatnot. And then we have, I wish I could read. The whole idea is we have to compactify these things. And if we do, then we get this 10 to the 500 solutions. So Lisa and Arcani, they have this other approach that people are pretty excited about. We wouldn't have to compactify them, but they don't say anything about these. What would happen with these? I haven't been able to find out what the deal is. You know, I think what they're saying is that they just model. They're just modeling the universe because they would have the same problem with the vacua, see, trying to find the vacua, and they can't do that. Well, all right, so this is what I wanted to spend a few minutes talking about dimensions. Let's just look at them for a minute. We know space dimensions are dimensions of movement, left, right, up, down, back and forth, right? And then we've got dimensions of velocity. The reason we want space in 3 dimensions is because we want to move. So we can describe a vector. You guys probably do this in school. Describe a vector so that we can move from one location to another. But that's a one-dimensional vector in a 3-dimensional space. And then we have dimensions in the sense of numbers where they're just powers of numbers, right? N squared is n times n to the third power is n times n times n, and so on. All right? So when we look at it then, this idea of one-dimensional motion in n-dimensional space, we can go back to classical motion. And just as we just described, you got the 3 observable dimensions of space and the 1 dimension of time. Quantum motion, you have the same thing, but then you got quantum degrees of freedom. So you calculate these quantum dimensions like spin and so on, but they're still within the 3 dimensions. You don't need extra dimensions of space to do that. At least they don't think. And then you get the string theory, and you got the 3 observables, but you got to add 22 unobservable dimensions of space plus 1 observable dimension of time for a total of 26 dimensions in all, and then you add supersymmetry to it to make it into superstring theory, and that's then down to the 10 dimensions, 11 with an M theory, and so there you have it. But the idea is that in order to make these equations come out and explain what's happening, they need more space to move. That's why you need more dimensions, right? So you got wiggly strings going around, little tubes, and all the different dimensions. But when we look at dimensions, look at what we've got. If you can consider this time, right? So that would be 1 dimension because it's a scalar, like time is a scalar, and then you got the line and the area and the volume. There's 4 dimensions right there. But they normally don't include this one. So when they talk about 4 dimensions, they go to hypersphere, but that's really the 5th dimension. And then they got another dimension, which would be the 6th dimension. And then the 7th dimension is this collineal manifold that they can fold off and make into. But see, this is where our observation, even mathematics, with what's called the Raoult-Bott periodicity theorem, there's no new phenomenon past this number. And of course, our observation tells us the same thing as well. All right? So the idea is then is that the first dimension, 0, is a scalar dimension, not a vector, and the contemporary particle physics needs to go beyond 1 plus 3. So here's 1 plus 3. They need to go beyond this barrier, and yet they need to stay in it. So that's why they have to wrap them up to explain why there can be so many. And still we don't see but this. And of course with the brains, the other idea is you can't detect it. It's out there. But it might as well be on the other side of the universe because we're like ants on a 2-dimensional surface. We don't know anything about the other dimension. So But it's really funny when we look at this in terms of numbers and geometry. If we look at the Greek tectactras, they really, you can't see this, it's cut off here, but 1 equals the Father, and 2 stood for duality, and 3 for unity because it brought the duality together, and 4 for completion. And but it was, you know, just like our bowling pins, we don't think about it when we go to the bowling alley, but you got 10 pins up there. But this is very sacred to them. And it turns out Pascal's triangle sees the same way. You can work out. It's really mathematically amazing. And this turns out to be Grassmann numbers where string theory lives. So this whole idea of 10 dimensions comes because they're dealing with the geometry and the mathematical relationships of this area. Now, when you go to the Clifford algebras, recognizing that there's 2 directions in every dimension, you can start with a point of 2 to the 0, and then, see, I'm going ahead of myself, that came up already, but, and then 2 to 0, 2 to 1, 2 to 0, 2 to 1, 2 to the square, 2 to 0, 2 to 1, 2 to 2, 2 to 3. It matches this in a way that really conforms to Euclidean geometry, where this is a point, mathematically it's the same as that point, this is a point in a line, this is a point, a line, in an area. This is a point, a line, an area, and a cube. All right? You can actually put those all together geometrically so that would be 2 to the 0. And then you'd have, I'll show you here. But here's what's interesting before we go on. Look at this. You can rotate this so it's easy, you know, symmetry. Maybe this is what happened when they provided this symmetry. But if you rotate this counterclockwise, so 2 to the 3 is up at the top, you get this, right? Now, it doesn't change the numbers, you can do it, but it makes it easier to see. 2 to the 3 is what? 8. And then you got 2 to the 4 is another 8. Then you got 2 to the first power, which is 2, so there's 6. And then you got 2 to the 0, which is 1, 2, 3, 4. What does that add up to? 26. 26. 26 and 10. Now, they're in there, see? Now, it's really interesting when we look at it this way. When you look at Grassmann numbers that they deal with in geometric algebra, the 1 is a scalar, all right? Then you've got the space. These are spaces. So this is a linear space. All these are linear spaces, they call them. And this is where they have to move, you see. But you got points that can move. Does this remind you of anything? By a vector, like a 1D brane, a 0D brane, a 2D brane, and a 3D brane. But here they're called vectors, bivectors, and trivectors in the mathematics because of the way they operate. And we'll talk about that at some point. But I thought you might see that connection there, very interesting. All right, so now we ask ourselves the question, can we unify the dimensions? Now remember, you guys that were here last time, what did we unify last time? With the help of the Xavier board. You remember? Pardon me? Units, yeah. The SI units, right? They're all a mess, but we were able to unify them in space and time, right? So now we're going to try to unify the dimensions. So let's start with a 0D point, which is the space of a point, which is our first dimension. And then what are we going to add to it? A line, right? So that's the second dimension. So now it gives us this linear, independent, linear space. The first 2 together, we got a middle like the Greeks liked it. See, they thought everything, first of all, you had the point, that was the Father, and then you had the duality, all right? So we're at the duality, but the point is still there. So you got something in the middle. They felt everything had to have a middle. But then we had the third one, what do we have? Well, that brings us to the space of an area, right? So now we've got 3 dimensions joined there, and then we add the third one, and that gives us the space of a volume, right? And so we've got all 4 dimensions in there. Now, you say, well, what point isn't time? Well, you know, maybe that's true, but just hold on for a minute. And the fact is that we're able to unify those things. We've got first, second, third, and fourth dimension. And remember, theorists always look for things they can unify, because if they can unify something, generally they can clarify something. All right? So, if we look at this first dimension within a three-dimensional frame, we can see that it has potential directions. It has 2 potential directions. Actually, it has lots of them. But but none of them are realized. So we can think of it as potential, right? And think of it as two numbers, one over the other, where one is the reciprocal. But if they're both the same, what's it equal to? 1. So it's still a point, right? But I put direction in quotes here. All right, so the point with 2 to the 0 is equal 1. So we'll consider 0 directions as 1. All right, then immediately, what do we have? When we go to the next direction, the second dimension has, if we add it, there are 3 one-dimensional directions, each with their inverse, right? See? Because we can go up and down, back and forth. These are all one-dimensional, right? Up and down, back and forth, left and right. All right, now if we add the second one, now you see, what have we got? These are two-dimensional. The arrow, of course, is one-dimensional, but it grows as 2 dimensions grow, right? So we can represent, now we haven't broken the symmetry or anything, we've still got perfect symmetry that we started with, but how many of those do we have? Two-dimensional magnitudes, we'll call it. We have 2 to the 2 equals 4. This is cut off. What does it say? It says, okay, yeah, there's 3 because of the Grassmann numbers. 1, 3, 3 at the bottom of the pyramid, right? 1, 3, 3, 1. So this is going to be 1, it's going to be 3, this is going to be 3. 3 times 2 the first, 2 each directions. So 1, 2, 1, 2, and 1, 2. And in the areas, look at the areas. See, now that gives us the planes. You can see 3 planes intersecting. Can you see them there? See, there's a plane that is in the center here, and then there's a plane here, right? That goes along orthogonal to it, and then there's a flat plane in the center that cuts through the center, right? So each one of those has 4, and there's 3 of them. All right, now, and we can put a truth table here that tells us what they are. It's x, y, and the inverses is minus x and minus y. So here's x, y, where x and y are positive, and here x and y are negative, both of them, right? And then we can go down through the rest of them, you see. And then finally, we can do that with the 3-dimensional ones, where we have 8. So it's 4 in 2 directions. All right. These weren't cut off. Can't read them, but there's a truth table over there, so we can do 4. Each one has its each one having its inverse for a total of 8. All right. So the 4th dimension then has 4 3D directions with inverses. Now again, these are 3D directions. These are 3D magnitudes. You see, if this thing were expanding, these would be independent. You could, okay, we can do it mathematically real fast. This is 2 to 2. This is a 2 by 2 by 2 stack of cubes, right? That gives us these extractions. So what's 2 to the 3rd? 8 cubes in there, right? You can see the 8. 1, 2, 3, 4, and then 4 on the bottom. All right, now if we go to 3, actually 4, because when we have to go out both directions at the same time. So we go out 2 more. We got 4. Now what's 4 to the 3rd?
48.
64.
64.
64. So 4 times 4 is 16, times 4 is 64. So, but they're going in independent directions, you see, as it grows bigger and bigger. So these are actually independent. So these are those spaces in that, and so when we put them all together, we got plus and minus 3 one-dimensional ones, plus and minus 6 two-dimensional ones, and plus and minus 4 three-dimensional ones. We add those up. What does that give us? 13 in 2 directions. 26 dimensions of motion. we didn't have to do any of this compactification or anything, or deal with brains or anything. We come up with this same number that they came up with early on in string theory. And we know that 10 is in there as well, because of the tectacris, the Greek tectacris, right? So who needs compactification? All right. So now what do we do?
Now, whose theory is this group? discussing that.
LRC theory. That's what we're working on with the LRC. So what we have here now is we've unified the space and time dimensions in the SI, which was really a lot of great progress. And now we've done this. We've unified these 4 dimensions to get 26 dimensions, but they're space and time dimensions. We're thinking of them as expanding, so there's nothing moving inside of them. They themselves are moving. This is a way to describe space and time. So, wow, pretty neat, huh? So now Peter Boyd, who wrote Not Even Wrong, Lee Smolin, remember, wrote The Trouble with Physics, the rise of string theory and the end of science, whatever it was. It caused so much. Those two caused a lot of brouhaha because they're saying that what string theorists are doing out here is just not science anymore. It's not predictable. It's just what they call pseudoscience. And so he's primarily a mathematician, and he's a professor at Columbia University. And so he asked, "What's next?" He says, "If no new evidence from the LAC comes, it will be many, what's it say there?
20
or 30 more years before we can build something even more powerful until we go significantly higher. We have to find other ways to proceed," he says then, right? Okay, so the mathematics of the standard model remains in many ways poorly understood. He's a mathematician. And he's saying this. "In particular, we do not understand all the representation theory of gauge groups." Well, you probably don't know much about gauge groups, but we can talk about that later on. And one indication of the problem with string theory is that it's not formulated in terms of a fundamental symmetry principle. Now, what we just looked at is formulated in very symmetrical, isn't it? I mean, any school child can see how symmetrical it is. And so their problem is they don't have any fundamental symmetry principle. They don't know what the group is. And we can talk about that later. All right, but finally he says maybe future progress will require not just unification of physics, but unification with mathematics. All right, and that is what we will talk about